Okay. Let's continue with chapter 22. I now have reference things for, I'm working on making some things to help you understand the right-hand rule. All right. Currently printing. But, so, just some basic announcements. For chapter 21, homework. Part 1 is due on the 11th. Part 2 is due on the 18th. Chapter 22 homework is due on March 11th. And next week we will have the exam. We will do review of chapters 19 through 21 on Monday, and the exam will be on Tuesday. And because we moved on Wednesday. My brain. The exam will be on Wednesday, and so it'll be at 2:30 on Wednesday. Any issues with that? Okay, all good. Started. So, if we look at, we've talked about magnetic force on a moving charged particle. Let's talk about magnetic force on a current carrying wire. So, force is charged times velocity cross magnetic field. So that's force is absolute value, magnitude of force is absolute value of charge times velocity times magnetic field times the side of the angle between them. For a charge carrying wire, the force on a charge carrying wire is also, the direction is determined by the right-hand rule, and the force is current times length times magnetic field times the sine of the angle. Current is, charge times velocity kind of thing. It's the rate at which charge is moving. Then there's the length over which the whole wire exists, which sort of tells you how much current times length ends up being equal to charge times velocity at some level. And then magnetic field sine theta. Because this is adding up the force from all the little individual particles through the wire. So current times length is the total charge that's moving times the speed that it's moving. And again, that moves with a right-hand rule. Point your fingers in the direction of the current, bend them in the direction of the magnetic field. Your thumb points in the direction of the force. So here's an example. We have a circuit with current. Remember, current goes from the positive terminal to the negative terminal. When the switch in this circuit is closed, the wire between the poles and the horseshoe magnet ends up deflecting downwards. So is the left end of the magnet a north magnetic pole or a south magnetic pole? Remember, magnetic field lines go out of north poles and into south poles. So, given you have a current going that way, And force going that way, which direction do you think the magnetic field is? Oh, I shouldn't have done that in blue. I will replace that with green. So we take our right hand, point our thumb in the direction of the force and our fingers in the direction of the current. When we curl our fingers, they point sort of out of the board or from here to here. So our magnetic field is that way. And so this is a north and this is a south. So the left end is a north pole. So here we have a copper rod that's 1.75 meters long and it has a mass of 0.0529 kilograms, and it's suspended from two thin flexible wires. And at right angles to the rod is a uniform magnetic field of 6.15 Tesla pointing into the page. And so find the direction and the magnitude of the electric current needed to levitate this copper rod. So what we want to do is we want to figure out what current we can run through this rod so it will levitate upwards. So remember, force is current times length times magnetic field times the sine of the angle. In this case, the angle is 90 degrees. The magnetic field is pointing into the phage. And you want to force a magnetic force that's upwards. And that magnetic force has to be big enough to counteract the weight mg of the rod. So Force of the magnet on magnetic force on a wire is current times length times magnetic field times the sine of the angle. In this case, that angle is 90 degrees, so the sine of the angle will be 1. The force of gravity is minus mg, and we want the total force to be 0. So first of all, direction. Magnetic field is into the page. Force is up. We want the current to flow to the right. Now let's figure out the magnitude. Current times length times magnetic field times sine theta equals mg, because FB equals FB minus mg equals 0. The current is going to be mg over the length times the magnetic field. So 0.0529 kilograms times 9.81 meters per second squared divided by 1.75 meters times 0.615 Tesla. That's 4.82 amps. You need to run 4.82 amps of current through this rod to levitate it in that magnetic field. So here we have a series of current carrying wires, and we want to rank them in magnetic field, in the same magnetic field. They all are in the same constant magnetic field, and we want to rank them in terms of magnetic force. So first one has length, has current of 1 amp and a length of ½ meter, and is at an angle of 0 degrees. Then we have 2 amps, 1 meter, angle of 30 degrees, ½ an amp, 2 meters, angle of 60 degrees, 0.1 amps, 4 meters, angle of 90 degrees. We want to rank these in terms of magnetic force. Well, we can go through and calculate the force for each one. Remember that magnetic force is current times length times B times sine theta. So for A, the force is 0, because the sine of 0 degrees is 0. For B, we have 2 times 1 times the sine of 30 degrees, which is 1/2. We get 1B. For C, we have 0.5 times 2 times the sine of 60 degrees, which is square root of 3 over 2. We get square root of 2 over 2B. And for D, we have 0.1 times 4 times 90 at 90 degrees. So the sine of 90 degrees is 1. That is 0.4B. So from weakest to strongest, D is the weakest, A is the weakest, then D, then C, and lastly, B is the strongest. Now, when you have a loop of wire in a magnetic field, that loop of wire will experience a torque. Because if you have current going around in a loop, the current is going in opposite directions on opposite sides of the loop. You can see here, the sides of the loop are going to experience forces that are equal in magnitude, but opposite in direction. Because on one side, the current is going down, and on the other side, the current is going up. And so, given the magnetic field is pointed this way, here the magnetic force is into the page. And here the force is out of the page. And here this is parallel to the magnetic field. So nothing happens there. Because they're not operating at the same point, they create a torque around the vertical axis of the loop. So you have a torque, and you can do some quick calculations to figure out what that torque is. So torque is going to be force times radius times sine of the angle between them. And the force is current. So assuming that we have something like this, where two sides are parallel, two sides are perpendicular, this is our current times length times magnetic field times, well, that's the force. And the radius is, half the width. So the torque ends up being 1/2 current times length times magnetic field, well, current times length times magnetic field times 1/2 width times the side of the angle this thing is at. But we have two forces. Each force is contributing this, so it's 2 times this. And so the torque ends up being current times length times width times magnetic field times sine theta, or current times area times magnetic field times sine theta. So the torque is, current times height times magnetic field times width over 2 plus current times height times magnetic field plus width over 2, which is current times magnetic field times height times width. And because area is height times width, torque is current times area times magnetic field when it's flat. And then there's a sign that ends up in that. In that particular image, that was 90 degrees. So if the plane of the loop is at an angle to the magnetic field, the general formula for torque ends up being current times magnetic field, times area times magnetic field times the sine of the angle between the normal and the magnetic field. And that is the torque that's exerted. And one of the ways we can increase that torque is by looping around multiple times. So you have a bunch of loops that are all applying torque. And so this ends up just being number of loops times current times area times magnetic field times sine of the angle. It's a torque. The units are Newton meters. And this is sort of what's going on in an electric motor. You're generating a torque by applying a current through a bunch of looped wires in a magnetic field. And the torque on a current loop is proportional to the current in it, which forms the basis of a variety of useful electrical instruments. So here, for example, is a galvanometer, which measures magnetic field. You can also use this to measure current. So here we have a rectangular coil with 225 turns that is 5 centimeters high and 4 centimeters wide. When the coil is placed in a magnetic field of 0.25 Tesla, its maximum torque, the maximum torque is just NIAB when the sign equals 1. Is 0.36 Newton meters. So what is the current in the coil? So, got a few minutes to work on this. Torque is N times R is N times current times area times magnetic field times the sine of the angle. Maximum current will be when the sine of the angle is 1. So maximum current is N times current, sorry, maximum torque is N current area magnetic field. So let's plug in our values. We want to find the current. We know the torque. We know N. Now this is that's N. We know the height and the width, so we can find the area. Here's our magnetic field. So, and we know the torque. So that's 0.36 Newton meters divided by 225 times 0.5 meters times 0.05 meters times 0.04 meters times 0.25 Tesla. And that gives you a current of 3.2 amps. So just continuing on with current loops. So we have two current carrying loops that are identical except for the direction of the magnetic field in their vicinity. Magnetic field at loop 1 is parallel to the plane of the loop, and the magnetic field of loop 2 is perpendicular to the plane of the loop. So loop 1 is sitting in a magnetic field that is pointing basically this direction. If the magnetic field is pointing this direction, loop 1 is like this. Loop 2 is like this. Loop 1 is like this. Loop 2 is like this. So is the magnetic torque exerted on loop 1 larger, smaller, or the same as that on loop 2? So loop 1 is parallel. Oh, sorry, I did that wrong. Loop 1 is like this. Loop 2 is like this. So loop one is like this. In the magnetic field, current is going around. Loop two is like this in the magnetic field. Current is going around. So which one has more torque? Loop two has more, so loop two has less torque. Because the angle for this, you get maximum torque when it's parallel. And the normal is perpendicular. Because, let's see if I can make a rectangle. If we have a magnetic field that's coming out of the board, current going around. So this side will go up, this side will go down when it's parallel. But when we get here, this side is pulling up, that side is pulling down. That's not making any torque. So what happens is when it's parallel to the magnetic field, the top and bottom are pulling apart and the whole thing doesn't really go anywhere. So an experimental observation that you can make is that electric currents can create magnetic fields. If you run a current through a wire, you find that iron filings will form circles around it. The compasses will go around in a circle around it. These fields form circles around the current. And there's a right-hand rule to figure out what direction the circles go. This is much easier. You take your right hand, point your thumb in the direction of the current, your fingers will curl in the direction of the magnetic field. So if I have a wire, I would basically grab the wire with my thumb pointing in the direction of the current. My fingers will wrap around the wire in the direction the magnetic field goes around it. So again, right hand. And the magnetic field is inversely proportional to the distance of the wire. So for a wire, is current over radius. Now, there's a constant there. We're going to get into what that constant. So the relation, so Ampere's law says if you take the path integral of the magnetic field dotted with the, as you go around, so ds, as you take a path around, so the parallel magnetic field summed up for each little segment of length, that will equal mu naught times I enclosed. That means for a wire with a current passing around it at a distance of r. This is mu naught over 2 pi. And mu naught is 4 pi times 10 to the minus 7 Tesla meter per amp. And that's an exact value. It is exactly 4 pi times 10 to the minus 7. Because the amp is defined by the force between two wires, and it turns out the force between two wires ends up being like 4 pi times like something. So the force, yeah, it works out that you get 4 pi. So we can use Ampere's law to find the magnetic field around a long straight wire. So B is theta naught times the current over 2 pi times the radius. That's the current around the wire. We can do similar things for other setups of current. And since a current carrying wire experiences a force in a magnetic field, and a magnetic field is created by a current carrying wire, if you have two current carrying wires, they will have a force between them. So if you have two wires whose currents are flowing in the same direction, they will be attracted to each other. If their currents are flowing in opposite directions, they will repulse each other. When you have enormous currents, this could actually be a problem. You can have wires and cables whipping around from the force between them. So because a current wire experiences a force in a magnetic field, that force is current times length times magnetic field. So current 2 times length times mu naught times current 1 over 2 pi d. So mu naught current 1 times current 2 over 2 pi d times the length. And that's how you end up getting, this number. So if currents are in the same direction, the wires will be attracted to each other. If they're in opposite directions, they will repel. So here, this is the magnetic field due to the current in this wire. So it's coming out of the board on the bottom and going into the board on the top. So what direction is this current flowing? Does it flow to the left or the right? So remember, if you stick a thumb in the direction of the current and wrap your fingers of your right hand will wrap in the direction that the magnetic field goes. So here, the magnetic field is going into the board on top and out of the board on the bottom. So if we curl our fingers, we want to go into the board above the wire and out of the board on the bottom. That means the current is flowing this way to the left. Here we want to find the magnitude of the magnetic field that is 2 meters away from a long straight wire that's carrying a current of 10 amps. This is again a fairly straightforward calculation. Magnetic field from a wire is mu naught current over 2 pi times the radius. That's 4 pi times 10 to the minus 7 Tesla meters per amp times 10 amps over 2 pi times 2 meters. The pi's cancel. 2 times 2 cancels with 4. You get 1 times 10 to the minus 6 Tesla. Here we have a 52 microcoulomb charged particle that moves parallel to a long wire with a speed of 720 meters per second. The separation between the particle and the wire is 13 centimeters, and the magnitude of the force exerted on the particle is 1.4 times 10 to the minus 7 newtons. So find the magnitude of the magnetic field at the location of the particle and the current in the wire. So for this, you're going to use the force equation. The angle will be 90 degrees, but the force is charge times velocity times magnetic field. You can use that to find the magnetic field. Once you know the magnetic field and you know the distance from the wire, you can use this formula for current in a wire, the magnetic field of a wire, to find the current. So let's start by finding the magnitude of the magnetic field. The force is the charge times the velocity times the magnetic field. So the magnetic field is the force divided by the charge times the velocity. So 1.4 times 10 to the minus 7 newtons divided by 52 times 10 to the minus 6 coulombs. So that's 52 microcoulombs times 720 meters per second is 3.7 times 10 to the minus 6 Tesla. So magnetic field at this point is 3.7 times 10 to the minus 6 Tesla into the board. The current is, we know the magnetic field is 3.7 times 10 to the minus 6 Tesla. The magnetic field is mu naught current over 2 pi r. So current is B 2 pi r over mu naught. So that's 2 pi times 1.3 meters, because it's 13 centimeters away from the wire, times 3.7 times 10 to the minus 6 Tesla. That's our magnetic field. divided by mu naught, which is 4 pi times 10 to the minus 7 Tesla meters per amp. Pi will cancel, and we get 2.4 amps. Any questions? Here we have two wires that are separated by a distance of 22 centimeters. They carry currents in the same direction. The current in wire 1 is 1.5 amps. The current in wire 2 is 4.5 amps. So what is the magnitude of the magnetic field halfway between the wires? So that means from current 2, that is coming out of the board. From current 1, it's going into the board. So they're going to partially cancel each other out. So what's the magnitude of the magnetic field halfway between the wires that are 22 centimeters apart? And they're carrying currents in the same direction. They'll partially cancel each other out. So let you work on that for a few. Good. So we have two magnetic fields in opposite directions here. The magnetic field from wire 1 and the magnetic field from wire 2. And the magnetic field for each is going to be mu naught times the current over 2 pi times the radius. And the radius is going to be half the distance between the two wires. The magnetic field from 1 is mu naught 4 pi times 10 to the minus 7 Tesla meters per amp times 1.5 amps divided by 2 pi times 0.11 meters. That's the 11 centimeters to the halfway point. So magnetic field 1 is 2.7 times 10 to the minus 6 Tesla into the screen. Magnetic field 2 is 4 pi times 10 to the minus 7 Tesla meter squared times 4.5 amps over 2 pi times 11 meters, but this will be out of the screen. So magnetic field 2 is 8.2 times 10 to the minus 6 Tesla out of the screen. That's 3 times as much. And so when we add them together, the total is going to be B1 minus B2 or B2 minus B1. This is 5.5 times 10 to the minus 6 Tesla out of the screen. Here we have two wires crossing at right angles that have the same current I passing through them. For points 1, 2, and 3, 1, 2, 3, and 4, state whether the magnetic field is strong, large in magnitude, or weak, small in magnitude. So I will draw in, so we can think about the magnetic field of each of these. So let's just go through it. Do you think the magnetic field at point 1 is strong or weak? That is correct. How about point 2?
Is it like comparing to the other two? Because
Yeah, well,
3 would be the strongest, and 4 would probably be second, or something like that. They would be like 3 and 4 would be stronger, and 1 and 2 would be.
that's not correct.
Oh.
So let me show you how it will work. So let's say, let's start with the vertical wire. So the vertical wire, we take our hand, we wrap it around. So that means for the vertical wire, the magnetic field of the vertical wire, I'll draw it in red. It is going into the board over here. And out of the board over here. Now we can do the other wire in green. Here we have this wire wrapping around. So it is going into the board on the bottom. And out of the board on the top. So over here in one is going into the board, one is going out of the board. They cancel each other out. This will have a minimal magnetic field at this point. Assuming it's the same distance from each wire, they have the same current that's given. It would cancel out completely, but it's going to be low over here because the magnetic fields are in opposite directions. They're canceling each other out. At 2, they're adding together. It's going to be large. At 3, it'll be small again because they're canceling each other out. And at 4, it'll be large. So 2 and 4 are big, 1 and 3 are small. And I think I'll go through the description of current loops and solenoids, and then we'll do that. So a current loop is similar to the magnetic field. The magnetic field of a loop of current is similar to the magnetic field of a bar magnet. And in the center of the loop, the magnetic field is N times mu naught times the current over 2 times the radius. And a solenoid is a series of current loops formed into the shape of a cylinder. And they have a strong uniform field inside the solenoid and weak, almost zero field outside the solenoid. And we can use Ampere's law to find the field inside of a solenoid because there's really only the field here. Everything else is 0. So magnetic field times length equals mu naught times I times the number of turns. So mu naught times number of turns over length times I is the magnetic field of a solenoid. And I'll go over that again next time. This is where we're going to start next time. I'm going to stop the meeting.